A beam of light departing from Earth takes more than 4 years to reach our nearest stellar neighbor. At the same speed, it would take exactly 100,000 years to cross our galaxy from end to end. So behind the iron bars woven by the laws of physics, we are completely imprisoned inside a cosmic prison. But what if these bars are crossed one day? Scientists are tracing the possibility of a method that could increase spacecraft to 10 times the speed of light and compress century-long journeys into decades. On this journey, you will encounter warp bubbles emerging in laboratories, foreign footprints hidden within gravitational waves, and the evolution of energy requirements that once seemed impossible into only insanely difficult. If you want to listen to reality, you can subscribe. Enjoy listening.
The fastest spacecraft ever built so far, the Parker Solar Probe, is tearing through space at a speed of 306,000 kilometers per hour. It sounds impressive until you calculate that reaching the nearest star at this speed would take 70,000 years. The journey in question would have begun in the last ice age and ended in a distant future. Humanity is trapped in a speed trap that rockets alone cannot solve. Light itself travels at a speed exceeding 1 billion kilometers per hour. Moreover, even closing the gap between us and Proxima Centauri takes 4.5 years. The diameter of our galaxy is 100,000 light years. Do the math, the number you will encounter corresponds to thousands of years. Every star shining in the night sky represents a target that is impossible to reach within a human lifetime with today's technology. The Voyager probes, launched into space in 1977, are today approximately 22 billion kilometers away from our home and have been traveling for nearly 50 years, yet they have not even fully escaped the gravitational influence of our solar system.
Here is the problem. Space is not only vast, but it is also actively mocking our ambitions. Interstellar distances are so enormous that even 99% of the speed of light turns interstellar missions into commitments lasting generations. When you set your course toward your destination, perhaps only your grandchildren's grandchildren will see you arrive there. Even worse, every existing propulsion system relies on the same fundamental principle: to move forward, leave something behind. Chemical rockets burn fuel. Ion engines eject charged particles. Nuclear engines expel heated gas. All of them obey classical physics. All of them crawl forward compared to the cosmic highway we must cross. Scientists call this the tyranny of the rocket equation. The more fuel you carry, the heavier your ship becomes. The heavier your ship becomes, the more fuel you need. In this nightmare spiral, fuel tanks eventually reach the size of entire cities, yet you can only reach a small fraction of the speed of light. We sent robots to Mars, we landed vehicles on the surfaces of distant moons, we photographed the boundaries of the observable universe, but we are still waiting in our own backyard, behind the bars. When Albert Einstein published the theory of special relativity in 1905, he wove invisible walls around humanity. His equations revealed something shocking. Nothing with mass can reach or exceed the speed of light. The universe enforces this rule through the very fabric of space-time itself. The reason appears deceptively simple. As objects approach the speed of light, they gain mass, and not just a little, but exponentially. A spacecraft approaching the speed of light would become heavier than entire galaxies. Accelerating it by just 1 kilometer per second more would require astronomical energy. This creates a cosmic catch-22. You need energy to accelerate mass, but acceleration increases mass, which requires more energy, which increases mass even further. The loop spirals toward infinity precisely at the moment you attempt to cross the threshold of light speed. Particle accelerators collide atoms at 99% of the speed of light and confirm Einstein's predictions with eerie precision. Objects truly become heavier. Time truly slows down. The rules are absolute. Time dilation makes things even more difficult. 99% of the speed of light pulls you into a different flow of time from everyone you left at home. A journey that feels like 10 years could last decades or centuries on Earth. When you return, you see that everyone you knew has long since died, and that the grandchildren of their grandchildren are now elderly people. The loneliness is complete and irreversible. Length contraction adds another distorted layer. At extreme speeds, space appears to compress in front of you. Years that must pass may shrink into months for you. In addition to all this, accelerating even a small object to the speed of light would consume the entire annual energy production of Earth within seconds. Even nuclear fusion, the process that powers the stars, is insufficient. If you converted the entire mass of a large asteroid into pure energy, it would barely be enough to carry a decently sized starship to a meaningful fraction of the speed of light. These are not engineering difficulties, they are fundamental impossibilities.
Earth may be dying, and we may have nowhere else to go. This cold reality keeps researchers awake at night, because when we look at the neighbors of our solar system, a bleak picture confronts us. Every other planet in the solar system is a desolate desert. Mars is nothing but a frozen desert where temperatures drop to -143 degrees Celsius. Its atmosphere is 96% carbon dioxide and so thin that standing on its surface is equivalent to standing 19 kilometers above Earth. Dust storms cover the entire planet for months. Since Mars lost its magnetic field billions of years ago, radiation from space mercilessly bombards the surface. Venus is even worse. Beneath its thick clouds, the surface temperature reaches 460 degrees Celsius, hot enough to melt lead. The atmospheric pressure is equal to the pressure felt 900 meters underwater on Earth, and the atmosphere itself consists of carbon dioxide mixed with sulfuric acid clouds. The probes sent to Venus survived less than 2 hours before being crushed and melted. There is not even a surface to stand on above the gas giants. The surface temperature of Titan, Saturn's largest moon, is -179 degrees Celsius, and you would freeze solid within a few unprotected seconds. Every body in the solar system is either too hot, too cold, or completely devoid of the basic conditions for life. Earth is not only our home. Considering current technology, it will remain our only habitable home for millions of years. That means if climate change, an asteroid impact, or any other catastrophe renders Earth uninhabitable, humanity has no backup plan. The idea of terraforming Mars, that is, making it habitable, does not go beyond pure speculation. Even the most optimistic estimates state that it would take thousands of years and require technologies we have not yet invented. That is why faster-than-light travel is not a luxury, but an evolutionary necessity. Telescopes have discovered more than 5,000 planets. Dozens of them are located in the habitable zone, where liquid water could exist. Proxima Centauri b, this planet only 4.2 light-years away, orbits within the habitable zone of its red dwarf star, and early data already points to a magnetic field. The TRAPPIST-1 system, discovered in 2017, is a system 39 light-years away, where 7 Earth-sized planets exist together, 3 of which are located in the habitable zone. Kepler 452b, on the other hand, is referred to as Earth's cousin and is 1,400 light-years away.
When Miguel Alcubierre sat down in 1994 to calculate whether faster-than-light travel was possible in real physics, he published a paper that divided his colleagues in two, because his mathematics was not only creative, but also technically correct. The Alcubierre drive, instead of accelerating a spacecraft through space, bends space around the ship. Space contracts in front of the ship and expands behind it. This asymmetry creates a wave that carries the bubble forward. The ship inside remains completely motionless relative to the space around it. It feels no acceleration at all. Think of it like a surfer riding a wave. The surfer does not outrun the water, nor create his own speed. The wave itself does all the work. Alcubierre's equations described a spacecraft surfing space-time in the same way. The clever part is that it exploits a loophole in Einstein's equations. Relativity says that nothing with mass can move faster than light through space, but Einstein never said that space itself cannot move faster than light. Space is already moving faster than light at the boundaries of the observable universe. Why not use this feature? Alcubierre's equations make it possible to create a negative energy density in front of the ship, causing space there to contract and to cause positive energy behind it to expand. The ship containing the bubble is propelled forward by this asymmetric space-time distortion. There is no thrust, no feeling of acceleration. The paper created deep echoes in physics. For the first time, someone had described a faster-than-light transportation mechanism using the accepted equations of general relativity. This was not speculative science fiction. It was a mathematical study that had passed peer review in a legitimate physics journal. The Alcubierre drive can theoretically reach any speed, 10, 100, 1,000 times the speed of light. Since the bubble does not move through space, relativistic effects such as time dilation and length contraction do not apply. Those inside experience a normal flow of time and do not age more slowly than those they left at home. Alcubierre himself admitted that he never expected the equations to produce this result. He was merely a physics student playing with equations inspired by a television series he loved. Yet the calculation he made almost playfully had revealed a real possibility embedded in the fabric of space-time.
The Alcubierre drive requires something that does not exist: exotic matter with negative mass and negative energy density. This is not antimatter, which creates an energy explosion when it comes into contact with normal matter. It is something far stranger. Instead of attracting, it repels, reversing the behavior of gravity. Normal matter bends space-time inward. Exotic matter bends it outward, creating a gravitational hill that pushes objects away. We have never observed this, measured it, or found evidence that it forms in nature. As if that were not enough, the required amount makes matters even worse. Alcubierre's initial calculations showed that bending space around a small spacecraft would require exotic matter equivalent to the total mass energy of Jupiter. Jupiter is 300 times heavier than Earth. Critics immediately pounced. Yes, the mathematics works, but demanding materials that do not exist makes the whole concept useless. It is like designing a perpetual motion machine powered by unicorn tears. The Casimir effect offered a small spark of hope. Two uncharged metal plates placed extremely close together in a vacuum attract each other due to quantum fluctuations, and the space between the plates technically possesses a negative relative energy density. This effect is measurable, verified, and real.
Dr. Harold White researched propulsion physics for years at NASA's Johnson Space Center. The new calculations he published in 2011 suggested that the energy requirements for the Alcubierre drive could be dramatically reduced. His revised mathematics showed that by optimizing the shape of the warp bubble, the energy requirement could be reduced by many orders of magnitude. Instead of exotic matter equal to the mass of Jupiter, a few hundred kilograms would be sufficient. Still exotic, still unattainable, but the concept had been moved from physically impossible to the realm of incredibly difficult. Then, in 2021, something unexpected happened. While White's team was studying the Casimir effect with specialized equipment designed to measure nanoscale forces between metal plates, the sensors detected something strange, a measurable space-time curvature at the nanometer scale. The readings matched theoretical predictions of what a small warp bubble would look like. They were not trying to produce a warp bubble, yet one had formed. The team repeated the experiment multiple times. The effect remained consistent and measurable. This meant a reproducible space-time distortion, created in a laboratory on Earth, measured, and made available for study. The warp bubble was microscopic, but real. This result created a bombshell effect in the propulsion physics community. Warp drive geometry was no longer purely theoretical. It could be experimentally produced, measured, and studied. If you can create a nanoscale warp bubble, enlarging it becomes an engineering problem, not a physical impossibility. Critics demanded verification. Other laboratories needed to confirm the results, and that would take time. Some physicists proposed alternative explanations for White's readings, perhaps electromagnetic interference, perhaps misinterpreted quantum effects. Healthy skepticism has its place in science. Nevertheless, White's team had carefully calibrated their instruments, accounted for known sources of error, and documented everything meticulously. Moreover, the effect appeared under the conditions predicted by the theory and disappeared when those conditions changed. This kind of correlation points to a real phenomenon rather than a measurement error. NASA quietly increased the funding transferred to White's laboratory. Other government agencies also took action. Private aerospace companies began hiring propulsion physicists to research warp field generation. Gravitational waves create ripples in space-time when massive objects accelerate violently. Colliding black holes, merging neutron stars, supernova explosions, all of them spread these ripples through the cosmos at the speed of light. We can now detect them with observatories such as LIGO and Virgo. In 2024, a research team from the University of Potsdam in Germany proposed a clever idea. Since warp drives bend space-time, they should also produce gravitational waves, and this pattern would be distinctly different from natural astronomical sources. The researchers ran simulations of exactly how different warp drive designs would appear in gravitational wave detectors. Then they began scanning existing data, searching for matches. Nothing was found in the current archives, but gravitational wave astronomy is still in its infancy. LIGO was only able to make its first detection in 2015. If there is any advanced civilization within a few billion light-years that has developed warp drive technology, we may detect the gravitational tremors left behind as they move their ships through space. The implications are dizzying. We may discover that faster-than-light travel is real, not by inventing it ourselves, but by detecting alien civilizations that are already using it. Faster-than-light travel terrifies some physicists because it could make time travel possible, and time travel creates logical impossibilities that threaten the consistency of reality. The grandfather paradox illustrates this perfectly. If you go back and prevent your grandfather from meeting your grandmother, you are never born. If you are not born, you cannot go back. If you cannot go back, your grandfather meets her after all. If he meets her, you are born. If you are born, you go back. An infinite loop with no consistent solution. Stephen Hawking proposed the chronology protection conjecture. Unknown physics prevents time travel even if the equations allow it. When someone attempts to create a time machine or a faster-than-light vehicle, quantum effects intervene. On the other hand, some scientists argue that warp drives, due to their geometries, may naturally avoid paradoxes. The space inside the bubble moves faster than light relative to the outside, but nothing locally surpasses the speed of light barrier. Information may not be able to cross the bubble boundary, which dramatically separates different regions of spacetime. The bubble functions as an insulating barrier that prevents problematic information flow. None of this has been confirmed. The honest answer is this: we do not know whether faster-than-light travel creates paradoxes, because we have never achieved it. The inside of a warp bubble would feel completely ordinary. You would not be able to tell whether the bubble was moving at 10 times the speed of light or perfectly motionless. The physics inside would function exactly the same as physics on Earth, because space-time remains flat and undisturbed. The extreme curvature occurs only at the boundary, creating a protective shell of normal reality around you. Your clock ticks at the same rate as clocks on Earth. Your cells age naturally. Chemical reactions proceed at standard rates. Light moves at its usual speed within the bubble. Looking from the outside, however, would present strange visuals. The light from the stars ahead of you would be massively blue-shifted due to space-time contraction, compressed into gamma rays. The stars behind you would shift into radio waves, into the infrared. The visible spectrum would transform into a distorted, stretched cosmic landscape, narrowed into a ring around your direction of travel. More importantly, warp drives eliminate the entire nightmare of acceleration. Trying to push the human body to extreme speeds with conventional propulsion produces forces that would collapse biological tissue. Pilots can endure up to 9 Gs without losing consciousness. Reaching even 1% of the speed of light within a reasonable time would require thousands of Gs of sustained acceleration. Bones would break, blood vessels would rupture, the brain would be crushed against the inside of the skull. The warp drive solves this completely and elegantly. The ship inside the bubble never accelerates, zero gravitational force. While space moves around you, you remain in place. Your coffee does not spill. Your stomach does not drop. Your body experiences no stress. This is not magic, it is geometry. Theoretically, an instant transition from a stationary state to 10 times the speed of light would create zero physical sensation. The transition would be imperceptible for everyone inside the bubble. The acceleration happens to space-time, not to your ship. This makes warp travel not only fast, but truly comfortable and safe for everything fragile. You could carry any equipment without special reinforcement. Delicate experiments could continue operating in transit. Passengers could walk, eat, and maintain normal activities. All of this stands in sharp contrast to relativistic travel, where almost everything becomes impossible. Now we come to the real question. None of these advantages matter if we cannot actually build it. 3 different warp drive concepts have emerged as the most promising candidates. Each approaches the same fundamental problem in a different way. The Alcubierre drive is the most well-known. Recent optimizations by Harold White and others have dramatically reduced the energy requirements. The challenge lies in whether large-scale Casimir effects can be scaled up through resonance phenomena. If you can create reinforcing standing waves of negative energy density, the total effect could reach usable magnitudes even if individual Casimir forces remain small, just as opera singers can shatter wine glasses through acoustic resonance, amplifying small vibrations into destructive forces. The Notario drive offers improved stability through smoother space-time distortions instead of sharp boundaries. It distributes the concentrations over a larger volume. This might be achieved without exotic matter, through carefully shaped electromagnetic fields or plasma configurations that create the correct energy density gradients. The third and less publicized approach involves directly exploiting dark energy. If you could locally concentrate or manipulate it, you could produce warp effects without requiring exotic matter or Casimir amplification.
Progress at every step occurs incrementally. Every laboratory success, no matter how small, confirms pieces of the theory and suggests paths forward. Every simulation identifies parameter ranges worth exploring or dead ends to avoid. The field is slowly moving from pure speculation toward engineering reality. No one knows which approach will succeed first or whether an entirely different concept will unexpectedly work better. This competition between rival designs fuels innovation. Research groups follow different paths, hoping to prove their strategy is the most viable. Current warp drive research is conducted with budgets measured in millions per year across all programs worldwide. Fusion research receives billions of dollars. The Manhattan Project spent $27 billion over 4 years in today's money. Apollo consumed $150 billion. If humanity committed such resources to warp drives, decade-long timelines could become realistic. Without that commitment, progress will remain slow. Yet among researchers, some privately admit that a single critical breakthrough could change everything overnight. Faster-than-light travel would fundamentally transform what humanity can become. Every great migration in our history, from Africa to all continents and across oceans to new worlds, expanded our potential and forced us to innovate. The stars represent our next frontier, but only if we can reach them. With warp drives, the galaxy opens. Hundreds of potentially habitable planets within 50 light-years become reachable destinations. If catastrophe strikes us, we could establish colonies in multiple star systems, ensuring humanity's survival. We could evolve from a species bearing single-planet risk into a multi-world civilization with redundancy and resilience. The economic implications stretch the imagination. If you can travel to and from the asteroid belt within hours, asteroid mining becomes routine. Rare elements abundant in other solar systems could be extracted and brought back. Direct study of alien ecosystems, close observation of star formation, first-hand investigation of black holes become possible. Every new world visited would rewrite textbooks and challenge assumptions.
Cultural transformation seems inevitable. A humanity spreading to the stars will diversify in ways we cannot even imagine. Isolated colonies adapting to their worlds will develop unique traditions, languages, and societies. The risks cannot be ignored. Warp drives may enable terrifying weapon systems. Space warfare could reach scales that dwarf Earth's conflicts. The environmental consequences are unknown. Does intense warp travel damage space-time? Could cumulative side effects reach dangerous levels? The answers to these questions require research before deploying the technology widely. Perhaps the scientists performing these calculations, measuring nanoscale distortions and running quantum simulations, are pioneers who continue their research, knowing that the reward may benefit only future generations decades from now. This kind of thinking built everything great our civilization has achieved. The universe is unimaginably vast. Light coming from the edge of the observable cosmos has been traveling toward us for more than 13 billion years and will never arrive, because the universe expands faster than light can traverse it. Warp drives do not change these cosmic limits, but they make the nearby galaxy, containing billions of worlds, accessible within the span of human lifetimes. This is the prize we are chasing, not infinite reach nor godlike power, but simply the ability to explore a few neighboring stars within a lifetime and to spread humanity among the stars. This future is being written right now in laboratories, through an equation, an experiment, a lifetime devoted to a breakthrough.
and perhaps it may arrive much sooner than any of us think.